extend the analysis of the previous example to vector addition of electrical forces in a plane. So we'll start with two equal positive charges, each with a charge of 2 microcoulombs, that are located on the y-axis as shown in this diagram. They're positioned symmetrically about the origin, so Q1 lies at a position of y equal 0.3 meters, and Q2 at a position minus 0.3 meters. We then place a third charge, position of x equal 0.4 meters, on the x-axis. And we want to calculate the net force on this third charge due to the proximity of these two charges. First thing we note is that by the geometry of the arrangement, this is going to be a right triangle with a side of 0.4 meters, 0.3 meters, and by the Pythagorean theorem, the hypotenuse, or the distance between, let's say, Q1 and the third charge, big Q, is 0.5 meters, as it is here. Now let's consider the free body diagram of the charge Q. There are two forces acting on it. One's a repulsive force from Q1. That force acts along a line connecting the two charges, as shown here by this arrow. And there's a similar repulsive force due to Q2 that acts along the line connecting them, as shown here. If this angle is alpha, then this angle is alpha, and we can get this angle because we have the sides of this triangle. Now the magnitude of these two vectors are given by Coulomb's law. And we can now calculate the size of those vectors. And so each of them is going to have a magnitude of 0.29 newtons. And the reason, of course, is that these two charges are the same distance from the charge in question. Now we can calculate the x components of these two forces. The x component of this force is going to be the magnitude times the cosine of this angle. But the cosine of alpha is adjacent over hypotenuse, 0.4 over 0.5. And so we'll get 0.23 newtons. The x component of the other vector is also the same value, 0.23 newtons. The two y components are the opposite of each other. They in fact cancel by inspection. So the net force is only in the x direction, and these two components add together and we get 0.46 newtons. So the total force on Q is in the positive x direction with a magnitude of 0.46 newtons. Notice, because of the vector nature of the electrical force, that this force, the net force, does not lie either on this line or on this line, but in fact lies on the x-axis.